All right. Good evening or afternoon there, everyone. I'm going to record lecture 29 here. So when we left off in the last lecture, we were talking about the factors influencing nucleophilicity. And we said that if you're comparing nucleophiles where the reacting atom is the same, so like oxygen-based nucleophiles, the nucleophile with the conjugate acid that is least acidic is going to be the best nucleophile. Another way to say that is that the most basic species is going to be the best nucleophile. And then we also said that when you go across a row, as you go to the right, the nucleophilicity decreases, okay? But what to do when you're going sort of vertically across the periodic table. And this is where solvent effects play a critical role. So in other words, if I'm trying to discuss the nucleophilicity of iodide versus fluoride, I can't have that discussion without knowing what solvent I am in, okay? And so we'll spend a little bit of time here talking about solvent effects on nucleophilicity. And so this is going to come into play, or just say it is important or necessary Okay, so it is necessary to consider the solvent when you're comparing nucleophiles in different rows. And so we'll start with polar protic solvents. And I'd also point you to table 9.6. Which has a lot of the data that I'm going to present. So we'll consider some generic reaction of a nucleophile with methyl iodide. Okay, and we said a polar protic solvent, so let's use methanol as our polar solvent, polar protic solvent. And so we end up with NuCH3 plus I minus, right? And so here are the here's the data. So for halogen-based nucleophiles, I minus, Br minus, Cl minus, and F minus, what we find is that the K-rels, the relative rates, are fastest for I minus, so 0.3, and then slowest for fluoride, so 5 × 10⁻⁸, and intermediate for chloride and bromide. So chloride is 3 × 10⁻⁶, and bromide is 3 × 10⁻⁵. Okay. And so iodide is going to be the fastest reacting nucleophile under these conditions, and fluoride is the slowest. Okay. And so what we're trying to do is going to try and understand this and make sense of it, okay? And like I said before, when we've got a collection of nucleophiles and it's the same atom that is attacking carbon, we can just look to pKa's. But that argument doesn't hold up here. So if you consider the pKa's of the conjugate acid, this is what you have. You have -10, -8, -6, and 3.2, right? And so whereas, for example, for oxygen-based nucleophiles, the conjugate acid with the highest pKa value, the least acidic species, is the most reactive. What we find here is that the least acidic species, in this case it would be HF, leads to the slowest reacting nucleophile, fluoride. So the pKa argument doesn't hold up here, right? And so this is the challenge with this chapter, is that we have sort of these explanations, but none of them are universal. But there is a way to think about this, and that is to consider the interaction of the nucleophile with the solvent, right? And so, we don't draw the solvent as a reagent in our reactions, but in fact, it is essential. And so we need to understand what these ions are going to look like when you put them in methanol, okay? And methanol, of course, is a polar protic solvent. The OH can serve as a hydrogen bond donor, and each of these anions can behave as an acceptor to some extent. So let me fill in some details here. So okay. Each of these halides is going to be able to interact with the methanol. And so the OH in methanol can serve as an H-bond donor. And my halide, which I'll just draw generically as Nu minus, can be an acceptor. And so the nucleophiles are going to be hydrogen bound, and they will be hydrogen bound to many molecules of solvent. For the sake of clarity in this discussion, I'm just going to draw it as one interaction, but this is not to imply that it's a one-to-one interaction. It's just to keep the drawings cleaner. So let me just write that down. So okay. So the answer to this question, the way we can explain these rates is if we can consider the relative strength of these H bonding interactions, okay? And that actually relies on knowing the pKa's. And so if we go to our pKa chart there, and we see that the HF is the least acidic conjugate acid of the nucleophiles. And so what that means in free energy terms is that fluoride is the least stable relative to its conjugate acid, okay? And what that means is that fluoride is going to bond, hydrogen bond, most strongly to any sort of polar protic solvent that is in its vicinity. And then at the other end, I minus, HI has a pK of -10. I minus then is very stable. And there isn't, by comparison, a strong driving force to hydrogen bond to solvent. In fact, those H bonds are very weak. And so what we can say is that the strength of hydrogen bonding correlates inversely with acidity. And so when I have fluoride in solution, that fluoride is going to H bond to the methanol, and this will be the strongest interaction in the halide series. And then at the other end of the spectrum, I've got I minus, and that too will H bond, but because I minus is so stable, this hydrogen bonding interaction is not very strong. And so this is the weakest H bonding interaction in the halide series. Okay, so let's take it a step further. So what does this mean? So, if I generate a bond, right, we know that bonds are stable, system loses energy. It's the same thing for a hydrogen bond, even though this isn't a full bona fide bond, that's a stabilizing interaction. You decrease the energy of the anion that is H bonding. And so if we think about what the relative energies of these species would look like, we can compare those energies in the gas phase and then also in methanol. So the column on the left here is going to be gas phase, so no intermolecular interactions. And then on the right, we'll say in methanol. Okay. And so we know that fluoride is the HF is the least acidic, so that's going to be the most reactive. And then that's going to be followed by chloride, bromide, and iodide, okay? But if we put these things into methanol, because the hydrogen bonding interaction of fluoride with the methanol is strongest, the energy of the fluoride drops by the largest amount, okay? And in a similar manner, the energy of Cl minus drops by a large amount. And you may be able to see where this is going. The energy of Br minus will drop, and then the energy of I minus certainly will go down, but not by much, okay? And so what we've effectively done when we put these halide salts into methanol is reshuffled their energies, reversed their relative energies. And so now I minus is the least stable. It's the one that is going to be most reactive. Fluoride, because it's hydrogen bound so strongly, is very stable now, and it's going to be very recalcitrant towards reaction. Another way to think about this is that, I am essentially burying the fluoride in a very large number of strong hydrogen bonds. And in order for the fluoride to react with my substrate, I need to start to break up those hydrogen bonds as it approaches the substrate, okay? And so that's like, you're going down, you've got all the H bonding. To get it to react, you've got to sort of re-emerge from that H bonding so that it can attack the substrate. And because fluoride is in such a deep well, that's going to slow down the reaction quite significantly. For iodide, iodide doesn't really care about H bonding. It doesn't cost that much to break up those H bonding interactions. And so you can very readily have I- attacking the substrate and without any sort of energetic penalty, okay? And so basically, to summarize, H bonding to solvent puts F minus in energetic well, or to be a little more scientific, minimum reaction with substrate requires us to disrupt the H bonding. And this of course costs energy. Okay, so polar protic solvents, I minus is going to be the most reactive halide. Okay, but then let's turn the page and consider the situation in a polar aprotic solvent, and we'll use dimethylformamide for that. So. Okay, so just to remind you, this is the structure of, oops, that is not the structure. This is the structure of DMF. Okay, it is a very polar solvent, but it doesn't have any hydrogen bonds. It does not behave as a hydrogen bond donor. Okay, so let's consider again, same reaction, nucleophile plus methyl iodide in now DMF as solvent goes to NuCH3 plus I minus, okay? And so we're gonna have the same type of table where we have our nucleophile I minus, Br minus, Cl minus, and F minus, and then pKa's I'll put here. Minus 10, minus 8, minus 6, 3.2, right? And then the K-rels, 0.4, 1.3, 2.5, greater than 3, okay? And so in other words, in a polar aprotic solvent, the relative reactivity is reversed. And so fluoride is the most reactive. And iodide is the least reactive. Okay. I'm just checking something here. And so, so now our fluoride is much more reactive. The other thing I want to point out is that the range here, the dynamic range, if you will, is much narrower. So we went, 8 orders of magnitude in methanol. Here, we're within about 7-fold in terms of the relative reactivity. So it's much closer, but fluoride is still the most reactive. And so why is that the case? How do we explain that? So what we say is that, fluoride, because HF has the most positive pKa value, fluoride is the least stable anion, okay? And we don't have any interactions with solvent that can selectively stabilize the fluoride. So if you remember, and I encourage you to go back to the earlier lectures, when we discuss solvent, when you put some sort of salt into a polar aprotic solvent, the cation gets strongly solvated, but the anion doesn't have as many intermolecular interactions. And so, for example, if we did sodium fluoride and put that in DMF, the interactions would look something like this. You'd have your sodium cation, and that would be stabilized by the DMF. Okay, but the F minus is still going to be solvated, surrounded by molecules, but you don't have a discrete sort of donor-acceptor interaction with solvent. So okay, and so you wind up essentially sort of faithfully reproducing the gas phase energies of the anions, in solution. So you're going to move everything, but they all sort of get moved and the relative energies don't change. And so in this case, in a polar aprotic solvent, the reactivity tracks very cleanly with the pKa. The least stable anion is going to be the most reactive. All right. So I'm going to pause here so we can break this into 2 parts, and then we're going to end with polarizability, which is the last little bit about nucleophilicity that I want to talk about. And then we'll start the E2 reaction. All right.